The spacecraft is dying. 15 billion miles above your head right now, a machine built in the 1970s
I
is
was
running out
wrong.
of
I
time.
admit that now.
The temperature
But I
is
learned from it, and that's
455
what
degrees
matters.
below zero. The power supply,
Hey
three
there,
lumps
little
of
one. You're so
plutonium
perfect.
generating electricity from
I've
radioactive
got you.
decay, has been fading for decades.
Team,
Every
anomaly
year,
in Sector
4 watts
7.
less.
Lock it down now.
Every
On
year,
it. Rerouting
another
power.
system shut
Confirmed.
down
Data
to
stream
conserve what
stabilizing.
remains.
Coffee's kicking in.
But it's still transmitting. A signal leaves the spacecraft. 23 watts of power. Weaker than the light bulb in your refrigerator. It travels through the vacuum of space at the speed of light. 22 and a half hours later, that signal reaches Earth. By the time it arrives, it's so faint that the most sensitive antennas humanity has ever built can barely detect it. 1/quintillionth of a watt, the faintest whisper we routinely hear from the cosmos. And what that whisper has been telling us for 50 years has shattered every prediction we made about where our solar system ends. Not slightly wrong, not close, but imperfect. 2.4 billion miles wrong. This is the story of how two machines designed for a 5-year mission to study Jupiter and Saturn flew for half a century to the edge of everything we know. How they discovered that the boundary between our sun's domain and the rest of the galaxy was in the wrong place. The wrong shape, made of structures no one predicted could exist. 7 major discoveries. 7 times our best scientists said, "This is where the edge is. This is what it looks like. This is how we'll know when we cross it." 7 times they were wrong. But that's not a story of failure. That's a story of what happens when human beings refuse to stop asking questions. This will be complex, because reality is complex, but every piece matters. Every discovery builds on the one before. Take your time. By the end, everything will connect. You'll see the pattern, and you'll understand what it means that we sent 2 machines into the darkness, and they told us we didn't know our own neighborhood. Let's begin. The year is 1956. Most people have never heard of the solar wind. The sun, everyone knows, is a ball of nuclear fusion 93 million miles away. It gives us light. It gives us heat. It stays put in the sky more or less while Earth orbits around it. But a physicist at the University of Chicago named Harrison Webb is looking at numbers that don't make sense. He's studying the sun's corona, the outermost layer of the solar atmosphere. You can see it during a total eclipse, that shimmering halo of white light extending millions of miles into space. Beautiful, mysterious, and according to Harrison's calculations, impossibly hot. The surface of the sun is about 10,000 degrees Fahrenheit, hot enough to vaporize any known material. But the corona is 2 million degrees. This violates basic physics. When you move away from a heat source, things should get cooler, not hotter. It's like walking away from a campfire and suddenly bursting into flames. Harrison sits in his office, the numbers spread across his desk. He's 50 years old. Thin, tall, with the kind of intense focus that makes people uncomfortable at dinner parties. He has a reputation for being stubborn, for following mathematics wherever it leads, even when it leads somewhere no one wants to go. And the mathematics is telling him something impossible. If the corona is that hot, the sun's gravity can't hold it. The gas should be escaping, streaming outward into space in all directions all the time. A continuous wind of charged particles, protons and electrons flowing from the sun at hundreds of miles per second. He runs the calculations again, and again, the answer doesn't change. There should be a solar wind, a river of plasma pouring out of the sun, filling the solar system, flowing past Earth, past Mars, past Jupiter, out to where Harrison stops. His pencil hovers over the page. If the sun is constantly losing mass, streaming particles outward in all directions, that wind has to hit something eventually. Space isn't empty. Between the stars, there's gas, extremely thin, about 1 atom per 10 cubic centimeters. For comparison, the air you're breathing right now has 10 to the 19th atoms per cubic centimeter. Interstellar space is 10 to the 19th times less dense than air, a better vacuum than anything we can create in our best laboratories. But it's not nothing, and the galaxy is moving. No, we're moving through the galaxy. The sun, the Earth, the entire solar system orbiting the galactic center at about 490,000 miles per hour. From the sun's perspective, the interstellar medium is a headwind. Thin, yes, but blowing past us at 500,000 miles per hour. So here's the question Harrison writes in his notebook. Where does the solar wind meet the interstellar medium? Where does the sun's influence end? He publishes his theory in 1958. The paper is called Dynamics of the Interplanetary Gas and Magnetic Fields. Dry title, Revolutionary Implications. He predicts that the sun is constantly ejecting a wind of charged particles, that this wind creates a bubble around the solar system, a region of space dominated by the sun. And somewhere out there, far beyond the planets that bubble, has to have an edge. The scientific community is skeptical. Some colleagues tell him the solar wind must be intermittent, only during solar storms, not constantly. Others say the mathematics is too speculative. One reviewer writes, the theory is interesting but lacks experimental confirmation. Harrison doesn't argue. He's a mathematician. He's shown what the equations demand. Whether the universe actually works that way, that's someone else's problem. But he writes in the margin of his personal copy, give it time, we'll measure it eventually. He doesn't know it yet, but he's just asked the question that will drive two spacecraft to the edge of the solar system and beyond. The solar wind exists. Spacecraft in the early 1960s confirm it. Instruments detect exactly what Harrison predicted, a constant stream of protons and electrons flowing from the sun. About 1 million tons of material per second streaming outward at speeds between 250 and 500 miles per second. 1 million tons sounds like a lot, but the sun is so massive that it would take trillions of years to lose even a fraction of its mass this way. The wind is real. The wind is constant. And the wind is supersonic. That last part matters. When something moves faster than sound, faster than pressure waves can propagate through a medium, you get shock waves. You've heard sonic booms when jets break the sound barrier. Same principle. In the solar wind, the sound speed is about 30 to 60 miles per second. The wind itself is moving at 250 to 500 miles per second. That's 5 to 10 times the speed of sound in the plasma. Supersonic flow. And when supersonic flow encounters an obstacle, it creates a shock wave ahead of the obstacle. The flow suddenly slows down, compresses, heats up. The shock wave is where the smooth, fast-moving stream becomes turbulent and slow. By the 1970s, Harrison has refined his predictions. He's now 65 years old. His hair is white. His office at the University of Chicago is filled with papers, blackboards covered in equations, half-drunk cups of coffee gone cold. He's calculated where the solar wind should create its first shock wave, about 75 to 90 astronomical units from the sun. 1 astronomical unit is the distance from Earth to the sun, 93 million miles. So 75 to 90 astronomical units means about 7 to 8.5 billion miles. This shock wave, he calls it the termination shock, is where the solar wind slows from supersonic to subsonic, where it hits the pressure of the interstellar medium and suddenly loses its smooth outward flow. Beyond the termination shock, there should be a region called the Helios heath, a turbulent zone where the slowed solar wind is trying to flow around the obstacle of the interstellar medium, like water flowing around a rock in a stream. And beyond the Helios sheath, about 10 to 20 astronomical units farther out, should be the heliopause itself, the place where the sun's influence ends. The place where the pressure of the solar wind equals the pressure of the interstellar medium. The place where our solar system stops being our solar system and becomes the galaxy. Harrison predicts the heliopause will be at about 90 to 100 astronomical units, somewhere around 8.4 to 9.3 billion miles from the sun. He publishes these predictions in multiple papers. He gives lectures. He trains graduate students. By the mid-70s, his calculations are in textbooks. The termination shock at 75 to 90 astronomical units. The heliopause at 90 to 100 astronomical units. A roughly spherical bubble may be elongated a bit like a comet's tail in the direction opposite the sun's motion through the galaxy, but basically symmetric. He's confident. Mathematics doesn't lie. The equations are well established. Magnetohydrodynamics has been studied for decades. The physics of shock waves and plasma dynamics is understood. He might be off by a few astronomical units here or there. Solar activity varies. The interstellar medium might be slightly denser or thinner than estimated, but the basic picture is solid. 75 to 90 astronomical units for the termination shock, 90 to 100 astronomical units for the heliopause. He'll be proven right. Just a matter of time. Just a matter of sending something out there to measure it. In his notebook, he writes a single sentence, 85 astronomical units. Mark my words. He underlines it twice. 1977. Something extraordinary is about to happen. A planetary alignment that occurs once every 176 years. Jupiter, Saturn, Uranus, and Neptune are arranging themselves in a specific configuration that allows a spacecraft to visit all 4 in a single journey. Without this alignment, visiting the outer planets would require separate missions. Too much fuel, too much time. But with the alignment, a spacecraft can use gravity assist, slingshotting from one planet to the next, borrowing momentum, accelerating for free. NASA calls it the Grand Tour. The plan is to launch 2 spacecraft, Voyager 2 on August 20th, Voyager 1 on September 5th. The names reflect their arrival order at Jupiter, not their launch sequence. Both are identical. Each weighs 1,820 pounds. They stand 12 feet tall. They carry a suite of instruments designed to study the giant planets: cameras, spectrometers, magnetometers, plasma detectors, cosmic ray instruments. The mission is supposed to last 5 years. That's what the engineers designed for. 5 years to reach Jupiter and Saturn, take measurements, send data back. After that, the spacecraft will drift into the outer solar system as the power fades and instruments go silent. No one expects them to last beyond their warranty period. But there's a man at NASA's Jet Propulsion Laboratory in Pasadena, California, who has a different idea. His name is Marcus Aldrin. He's 43 years old in the summer of 1977. An astrophysicist with a face that seems perpetually caught between wonder and worry. He has dark hair starting to gray at the temples. He speaks softly, but when he talks about the cosmos, his voice gains intensity. Conviction. Marcus is sitting in a conference room at JPL. It's April 1976, more than a year before the Voyager launches. 14 people around the table. A budget meeting, dry stuff, instrument manifests, weight allocations, power budgets. Marcus stands up. He's holding something, a prototype, a gold-plated copper disc 12 inches in diameter. It gleams under the fluorescent lights. "I want to put this on Voyager," he says. The room goes quiet. "Dr. Aldrin," says the NASA administrator at the head of the table, a woman named Eleanor Walsh. "This meeting is about planetary science instruments." "Not what is that exactly?" "A message," Marcus says, "to anyone who might find the spacecraft, millions of years from now." Someone snorts. Marcus ignores it. 5 years, he says. That's the design life. But what if they don't die? What if they keep going? What if they last 10-year, 2050? What if they leave the solar system entirely and drift into interstellar space? They won't have power, someone objects. The RTGs will decay. The record will still be there, Marcus says. Gold doesn't corrode in a vacuum. The information, sounds, images, greetings from Earth will last for billions of years, long after we're gone, long after the sun dies. This spacecraft could be the only proof humanity ever existed. Eleanor Walsh leans back in her chair. "Dr. Aldrin, this is a planetary science mission, not philosophy. What is science if not asking who we are?" Silence, Marcus continues. "We're going to spend $800 million to visit Jupiter and Saturn. Wonderful, essential. But these spacecraft won't stop at Saturn. They'll keep going, out into the darkness. And when they get there, if anyone is listening, what do we want them to hear? Silence or hope? The debate lasts 2 hours. Budget concerns, every gram counts. The disk adds weight. Power concerns, no, the record is passive, needs no power. Content concerns, what music represents humanity, whose humanity, which languages, what images. Marcus answers each objection, carefully, patiently. Finally, Eleanor Walsh calls for a vote. 8 in favor, 7 against, the narrowest possible margin. Marcus gets his record. He assembles a team, a linguist named Anna Kowalski to handle greetings in 55 languages, an ethnomusicologist named Mei Lin to select music from cultures around the world, a NASA liaison named James Holbrook, deeply skeptical but efficient. They have 14 months before launch. The arguments start immediately. Music selection becomes a battlefield. Mei Lin wants diversity: Javanese gamelan, Senegalese drums, Aboriginal songs, Peruvian panpipes. James wants Western classical: Bach, Beethoven, Mozart. These are mathematically sophisticated, he argues. Any intelligent species would recognize the patterns. Bach is brilliant, Mei Lin counters, but he's one culture, one era, one slice of humanity. We need to show we're more than that. Marcus mediates. Both, we include both. How much space do we have? 90 minutes, 27 pieces of music. They argue over every selection. Bach's Brandenburg Concerto No. 2 makes the list. So does Beethoven's Fifth Symphony. But also Blind Willie Johnson singing "Dark Was the Night, Cold Was the Ground." Chuck Berry's Johnny Be Good. Traditional music from Java, Zaire, Australia, Peru, Japan, India, China, Senegal. James Holbrook fights the Chuck Berry inclusion. Rock and roll. That's not humanity's best. Marcus looks at him. It's humanity's joy. That matters more than perfection. Well, Mei Lin adds, if we only send our best, we're lying about who we are. The vote 14-3. Johnny Be Good goes on the record. Then comes the images. 116 pictures encoded digitally. Mathematical definitions, the solar system, DNA structure, human anatomy, landscapes, architecture, People eating, working, playing, and human figures. Anatomically correct. The debate nearly destroys the committee. Pornography, someone says. Biology, Anna Kowalski responds flatly. Science. If they can build spacecraft and retrieve this record, they can handle human anatomy. Marcus makes the final call. The nude figures stay. A newspaper headline the next week. NASA sends nude photos to space. Marcus's daughter, Rebecca, 8 years old, asks him at breakfast, Daddy, why are people mad about the pictures? Marcus sets down his coffee, looks at his daughter, because truth makes people uncomfortable sometimes. But truth is more important than comfort. Will the aliens find it? Probably not, sweetheart. Space is too big. Then why send it? Marcus pauses. Long pause. He's looking at his daughter, but his mind is 15 billion miles away. Because trying matters. Reaching out matters, even if no one's there. Rebecca doesn't understand, not yet. But 30 years later, she will. She'll be an aerospace engineer herself by then. She'll remember this breakfast. She'll understand what her father meant, because by then Voyager will have done something no one predicted. There's one more thing Marcus adds to the record. Late one night, alone in the studio, it's 2 a.m, June 1977, 2 months before launch. The record is almost complete. But Marcus has reserved one 60-second slot. His wife, Catherine, is in the hospital. She gave birth 3 days ago. A boy. Their second child. They named him David. Marcus has brought recording equipment to the hospital. The nurses think he's insane. Catherine just smiles, exhausted, holding the infant. Marcus sets up the microphone next to the bassinet. He waits. 20 minutes. 40. The baby sleeps. Then at 2:47 a.m. David wakes. Starts crying. Marcus presses record. He captures 60 seconds of his son's heartbeat. The tiny, rapid pulse of a 3-day-old human. 140 beats per minute. Catherine whispers, why his heartbeat specifically? Marcus doesn't look away from the baby. Because when they listen, if they listen, I want them to know we felt this. That we loved. Catherine starts crying, quietly. Marcus labels the track Infant Heartbeat. He doesn't tell the committee it's his son's heart. It goes on the record. Somewhere in the gold grooves of that disc, spinning through interstellar space right now is the sound of David Aldrin's heartbeat. Still beating in a way, still alive in a way. Long after David himself will die. Marcus doesn't know it yet, but this will be his most personal gift to the cosmos. Not Bach, not Beethoven, not the greetings in 55 languages. The sound of his son's heart. Still traveling, still speaking, still saying we were here. We felt. We loved. August 20th, 1977. Cape Canaveral, Florida. Launch Complex 41. Voyager 2 sits atop a Titan 3E rocket. 363,000 pounds of fuel and machinery waiting to ignite. At JPL in California, Dr. Elena Vasquez sits in mission control. She's 36 years old. Red hair pulled back in a tight bun. Freckles across her nose. Hands steady on the console, but her heart is racing. This is her first time as lead systems engineer for a major launch. She's been at JPL for 8 years. Worked her way up from junior technician to this chair, this responsibility. On the console in front of her, telemetry from Voyager 2, power systems, guidance, communications, all green. But 3 days ago, she found something. A voltage fluctuation in the radioisotope thermoelectric generator, RTG2, the middle plutonium unit, 0.3% below nominal, barely noticeable, probably nothing. Except if it's not nothing, the spacecraft dies in 8 to 10 months instead of 5 years. Elena ran simulations, 72 hours of work, no sleep. Just coffee and mathematics. She found a workaround. Rewrote power through the backup converter. Upload the patch after launch during the trajectory correction window. She told no one. Not because she's hiding something. Because if she tells them now, they'll delay the launch. Run more tests. Maybe scrub the mission entirely. The planetary alignment won't wait. So she's sitting here hands steady, keeping a secret that could kill the mission. In her notebook, she's written, if they knew how close we came, they'd lose faith. Some secrets keep missions alive. T minus 10 minutes. The countdown proceeds. Elena watches every number, every reading. Power nominal. Guidance locked. Communications strong. T minus 60 seconds. She whispers to herself, fly true, baby. T minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Ignition. The Titan IIE roars to life. 7.5 million pounds of thrust. The ground shakes. The windows of mission control vibrate. On the screens, Voyager 2 rises. Slowly at first, then faster. Climbing through the atmosphere. The solid rocket boosters fall away. The core stage burns. The Centaur upper stage ignites. 12 minutes after launch, Voyager 2 is in space. Elena exhales. First hurdle cleared, but she knows the real test comes in 48 hours. When she uploads the power rerouting patch. When she finds out if her calculations were right. If they weren't, Voyager 2 dies before reaching Jupiter. She goes home that night, can't sleep, returns to JPL at dawn, uploads the patch during the trajectory correction window, waits 14 hours for confirmation. The telemetry comes back. Power systems stable. Voltage holding. The fix worked. Elena sits alone in her office. 3 a.m. puts her head on her desk. Whispers, "We're good. We're going to make it." No one hears. No one knows how close they came. And she'll keep it that way for 50 years. Until her final eulogy when she'll mention it. One sentence. "Even my first secret fix 3 days after launch couldn't save it from time." But that's decades away. For now, Voyager 2 is healthy, flying, heading toward Jupiter, and Elena has just saved the mission before it even began. September 5th, 1977. Voyager 1 launches. Same rocket, same trajectory but faster. It will overtake Voyager 2 and reach Jupiter first. Marcus Aldrin watches from the viewing stands with his family. Catherine beside him. Rebecca, 8 years old, bouncing with excitement. David, 3 months old, sleeping in Catherine's arms. The countdown reaches 0. The rocket ignites. Marcus watches it climb, become a star, become a memory. Rebecca tugs his sleeve. "Daddy, will the aliens find it?" Marcus looks down at his daughter. "Probably not, buddy. Space is too big." "Then why send it?" He's answered this before. But the answer deepens each time he gives it. Because trying matters. Reaching out matters. Even if no one's there. Rebecca thinks about this. But what if someone is there? Marcus smiles. Then we gave them the best of us. Music, greetings, pictures of home, the sound of a heartbeat. He doesn't tell her it's her brother's heartbeat. She'll learn that later. Much later. They watch until the rocket disappears. Catherine says quietly, "Do you think they'll make it?" "To Jupiter, yes." "I mean farther." Marcus looks at the empty sky where the rocket was. "I don't know, but I hope so." What he doesn't say, "I think they'll outlive all of us." What he doesn't say, "I think they're going to find something we can't even imagine yet." What he doesn't say, "I think Harrison Webb's predictions are wrong. And when Voyager proves it, we're going to learn something that changes everything." He just watches the sky. Somewhere above them, Voyager 1 is already 50,000 miles away, racing outward at 38,000 miles per hour. Heading toward Jupiter, heading toward Saturn, heading toward the edge Harrison Webb predicted, heading toward discoveries no one saw coming. March 9th, 1979, 3:47 in the morning. The navigation lab at JPL is mostly empty. Just one person. Dr. Rachel Dimitri, 28 years old, alone with the computers and the hum of cooling fans. She's not supposed to be discovering anything tonight. She's supposed to be doing math. Navigation engineers don't make headlines. They do calculations, orbital mechanics, trajectory corrections. Rachel is processing images from Voyager 1's Jupiter flyby looking for moon positions, numbers, coordinates, data to refine the spacecraft's exact location. She's been at this for 6 hours. Her coffee went cold at midnight. She didn't notice. Image 14 Jupiter. Io on the limb, perfect for measurement. She enhances the image to see the moon's edge more clearly. Standard procedure. Then she stops. Something's wrong with Io's silhouette. There's something extending from the edge. Into space, a plume, a cloud, an umbrella-shaped structure reaching up from the surface. Rachel stares at the screen. Artifact glitch. She runs verification algorithms, checks the raw data, processes the image 3 more times. The plume is real. Oh, yeah, it's you. 190 miles high, extending from Io's surface into space. She knows what this is. She knows what this has to be. But she stares at it for 11 minutes before she lets herself believe it. She times it later. 11 minutes of just looking. Because the moment she accepts what she's seeing, everything changes. Finally, she picks up the phone, dials her supervisor's home number. It's 4:23 in the morning. Dr. Gerald Hammond answers on the 6th ring. "This better be good, Dimitri." Rachel's voice is steady, surprisingly steady. "Io is erupting. Right now. Active volcanic." Silence on the other end. "Then I'll be there in 20 minutes. Rachel hangs up, sits back in her chair. She whispers to the empty room, I just found the first extraterrestrial volcano in history. The room doesn't answer, but the universe has just gotten bigger. The press conference is on March 10th, 2 p.m. Pacific time. 200 journalists packed into a briefing room at NASA headquarters. Rachel never wanted this. She's a navigation engineer. She does calculations in quiet rooms. She doesn't do spotlights. But here she is, standing at a podium, notes prepared by Marcus Aldrin. He's good with words. She's good with numbers. Fair trade. The room is loud. Flashbulbs. Questions shouted before she even starts. She grips the podium, starts reading. At 03:47 Pacific time on March 9th, I observed an umbrella-shaped anomaly extending approximately 190 miles from Io's surface. Her voice is shaking. Further analysis confirms this is a volcanic plume. Active eruption. The first active volcanism ever observed beyond Earth. The room erupts. Questions. Cameras. Chaos. Rachel loses her place in the notes. Finds it. Continues. She explains tidal heating, Jupiter's massive gravity. Europa and Ganymede pulling on Io. The moon's interior flexing, melting, erupting. Sulfur dioxide. Silicate lava. Temperatures hot enough to melt rock on a world 5 times farther from the sun than Earth. Her voice steadies as the science takes over. This is what she knows. This is where she's comfortable. Then someone from the New York Times asks the question she wasn't prepared for. Dr. Dimitri, what does this mean for the possibility of life elsewhere? Rachel stops. The room is silent, waiting. 8 seconds pass. Feels like minutes. She wasn't given talking points for this. This isn't about navigation. This isn't about orbital mechanics. But she answers, unrehearsed, honest. It means heat sources exist far beyond what we imagined. If Io can stay warm at Jupiter's distance through tidal forces, then Europa's subsurface ocean isn't speculation anymore. It's probable. And if there's liquid water under Europa's ice, she pauses. We might not be alone after all. The room explodes. Rachel realizes what she's just done. She's become the face of astrobiology. She didn't want this, didn't ask for it, but it's too late now. That night, the headline in every major paper, NASA discovers alien volcanoes. Scientist says we may not be alone. Rachel sits in her apartment, alone, looking at the newspaper. She whispers, I just did my job. But the universe doesn't care about job descriptions. It gives gifts to whoever looks closely enough. Voyager 1 spends 4 months in the Jupiter system. The discoveries cascade. Europa's surface is smooth ice crisscrossed with cracks and ridges. Very few impact craters, meaning the surface is young, recently renewed. The ice appears to have fractured and refrozen in complex patterns. Marcus Aldrin becomes obsessed. In meetings and hallways at lunch, he keeps saying it. There's an ocean under that ice. I know it. I know it. People are more cautious. We can't prove it. We can infer it, Marcus insists. The surface features, the tidal heating. Europa is getting flexed by Jupiter just like Io, but less violently. Not enough to create volcanoes, but enough to melt ice, to keep water liquid. It's speculation. Science is informed speculation, Marcus says. We speculate, then we test. The evidence is circumstantial but mounting. Fractured ice. Smooth regions where the surface has been completely renewed. Long linear cracks called lineae stretching for hundreds of miles. Chaotic terrain where the ice looks like it broke apart and refroze. All consistent with a subsurface ocean. Voyager can't prove it, but it suggests, it hints, it makes the idea plausible. 30 years later, the Galileo spacecraft will provide stronger evidence. Magnetic field measurements suggesting a conducting layer, salty water, beneath the ice. But that's the future. Right now in 1979, and all they have are images and interference by gammas. But Marcus is convinced, and he's usually right. Ganymede shows a complex surface, old dark terrain covered with impact craters, younger brighter terrain with grooves and ridges. Some kind of geological resurfacing happened in the moon's history. Something internal. Heat, or ice, or both. Callisto is different, heavily cratered, ancient, unchanged for billions of years. The oldest surface in the Jupiter system. And Jupiter itself has a ring, faint, made of dust-sized particles, nothing like Saturn's spectacular ice rings. But there, no one predicted it. The discovery is almost accidental, a long exposure image looking for faint moons. The ring shows up as a thin line. Elena Vasquez, watching from Mission Control, says what everyone's thinking. Every gas giant might have rings, Saturn's not special. A paradigm shift. Ring systems is the norm, not the exception. Voyager 1 leaves Jupiter in April, heading towards Saturn. The spacecraft has done what it was designed to do, studied the giant planet, made discoveries, sent data home. But it's still healthy, power good, instruments working, trajectory locked, 16 months until Saturn, and a decision waiting that will change everything. November 12th, 1980, Voyager 1 approaches Saturn, the ring giant, the most beautiful planet in the solar system. And sitting between Saturn and its moon Titan is a decision that will change the mission forever. The spacecraft can do a close flyby of Titan, skim just 2,500 miles above the surface, get incredible data on the only moon with a thick atmosphere. Or it can skip Titan and continue to Uranus and Neptune. Can't do both. The orbital mechanics don't allow it. Mission control debates for weeks. The meeting on November 8th is tense. 30 people in the room, scientists, engineers, administrators. Harrison Webb is there. 74 years old now, but still sharp, still engaged. He speaks carefully. Titan's atmosphere is unique. Nitrogen, methane, organic chemistry. We need that data. James Holbrook, the NASA liaison, counters. We'll lose half the grand tour. Voyager 1 won't see Uranus or Neptune. We'll only get one spacecraft at the ice giants instead of two. Elena Vasquez sits quietly. She's been running trajectory simulations for 3 weeks. She knows the numbers better than anyone. Finally, someone asks her directly, Elena, what's your recommendation? She takes a long breath. Voyager 2 can handle Uranus and Neptune. It's on the right trajectory. It's healthy. What about Voyager 1? Let it die at Saturn, Elena says quietly. But die learning everything it can. The room goes silent. Marcus Aldrin nods slowly. Choose depth over breadth. One perfect flyby of Titan instead of mediocre passes at 4 planets. The vote is 11-4, close Titan flyby, end Voyager 1's planetary mission. Elena uploads the trajectory commands on November 12th, watches the telemetry confirm. The course is locked. She murmurs to her console, "You're going to the edge now, straight to the stars." No one hears her. But Voyager 1's planetary mission is over. Its cosmic mission is just beginning. The Titan flyby happens on November 12th, 1980, 2,500 miles above the surface. Closer than any spacecraft has ever come to another world with an atmosphere besides Earth. The data comes back. Incredible. Overwhelming. The atmosphere is thicker than expected. Surface pressure, 1.5 times Earth's at sea level. Higher pressure than any other moon or planet except Venus. Composition, 95% nitrogen. Like Earth. But the other 5%, methane, ethane, propane, acetylene. Complex organic chemistry happening in the atmosphere. The surface is hidden. Opaque orange haze. Layers of photochemical smog created when sunlight breaks down methane. The cameras can't see through it. All they capture is the top of the haze layer. But the atmospheric data is extraordinary. Temperature at the surface minus 290 degrees Fahrenheit. Cold enough that water ice is rock hard, but warm enough that methane can exist as a liquid. There's a methane cycle, analogous to Earth's water cycle. Methane evaporates from the surface, forms clouds, rains back down. There are probably lakes or seas of liquid methane and ethane, rivers and streams flowing with liquid hydrocarbons, a surface shaped by erosion and deposition, organic chemistry driven by sunlight, complex molecules forming in the upper atmosphere, falling to the surface, accumulating over billions of years. Marcus Aldrin watches the data come in. He's standing in mission control at 3 in the morning. Can't sleep. Too excited. He says to no one in particular, another world with weather, with seasons, with a surface shaped by liquids. Someone nearby, but we'll never see the surface. Not today, Marcus says, but someday. He doesn't know it, but he's right. 25 years later, the Cassini mission will orbit Saturn for 13 years. The Huygens probe will land on Titan in 2005, return the first images from the surface, reveal a world of methane lakes, river channels, dunes made of organic sand, but that's the future. Right now, all they have is data and wonder, and Voyager 1 climbing above Saturn's rings, leaving the realm of planets behind, heading north of the solar system plane, accelerating toward interstellar space, toward Harrison Webb's predicted boundary, 85 astronomical units away, 22 years of travel time. The spacecraft will get there in 2002. And when it does, Harrison will discover that his life's work, his calculations, his predictions, his confidence was built on incomplete understanding. The boundary is not where he thinks it is. The boundary is not what he thinks it is. and the universe is about to teach him humility in the most profound way possible. December 1980. Elena Vasquez sits alone in her office at JPL 2 in the morning. Everyone else has gone home. On her computer screen, Voyager 1's new trajectory, a line extending beyond Saturn, beyond Uranus, beyond Neptune, beyond everything, pointing toward empty space. She's just sent this spacecraft to die exploring the void, but something tells her a feeling she can't name doesn't share that Voyager 1's real mission is just beginning, that everything they think they know about where the solar system ends is wrong, that in 22 years when the spacecraft reaches Harrison Webb's predicted boundary, it will find something else entirely, something no model predicted, something that will require them to rewrite the textbooks. She closes the trajectory file, sits in the dark, whispers, "See you at the edge." The spacecraft is 15 billion miles away by now, still accelerating, still healthy, still carrying the golden record with Marcus Aldrin's son's heartbeat encoded in the grooves. Still heading toward a discovery that will shake the foundations of everything they think they understand. But that's years away. For now, Voyager 1 is just a machine in the darkness, flying faster than anything humanity has ever built. Alone, silent, waiting. 22 years pass. Not in an instant, not in a blur. 22 years of patience, of waiting, of watching a spacecraft drift farther from home than anything human has ever traveled. Voyager 1 keeps flying, 38,000 miles per hour. Every day, another 912,000 miles farther from the sun. Every year, another 3.6 astronomical units deeper into the outer solar system. The spacecraft ages. The power output from the radioisotope thermoelectric generators declines steadily, 4 watts per year. Every year, the engineers calculate how much longer. How far can it go before the plutonium decays too much, before the electricity drops below the threshold needed to keep the transmitter alive? But it keeps transmitting. The planets are far behind now, Neptune. The last one Voyager 2 visited in 1989 is 30 astronomical units from the sun. Voyager 1 passed that distance in 1998, kept going. By 2001, the spacecraft is 79 astronomical units from the sun, 7.3 billion miles. The signal takes 11 hours one way to reach Earth, 11 hours traveling at the speed of light through the vacuum of space. And Harrison Webb is waiting. He's 75 years old now, retired from the University of Chicago, but still active, still publishing, still refining his predictions. His hair is completely white. His hands shake slightly early, Parkinson's, the doctors say, but his mind is sharp. He knows the numbers. Voyager 1 should hit the termination shock any month now. The boundary where the supersonic solar wind slows down, where it hits the pressure of the interstellar medium and creates a shockwave. Harrison has predicted this shock will occur at 85 astronomical units. He's been saying this for 30 years. Published papers, given lectures, trained students, written textbook chapters. The number's canon now. 85 astronomical units, plus or minus 3 for solar cycle variations. The spacecraft is at 79 astronomical units, 6 astronomical units to go, about 2 years. Harrison calls JPL every month, asks Elena Vasquez, she's 60 now, senior engineer, still the one who knows Voyager best if there's any sign yet. Not yet, Harrison, she tells him, but soon. 85, he says, mark my words. She doesn't argue. Harrison's mathematics are impeccable. The physics sound. If anyone can predict where the solar wind meets interstellar space, it's him. But something about his certainty makes her uneasy. In her experience, the universe doesn't care about our certainty. August 1st, 2002. Voyager 1 is at 85.1 astronomical units. The plasma wave instrument, designed to detect oscillations in the charged particle environment, registers unusual activity, a sudden jump in certain frequencies, the kind of signature you'd expect from particles being compressed and heated. A shock wave. The data comes down. 11 hours after the spacecraft detected it, the team analyzes, cross-checks, runs the numbers. It's the termination shock, right where Harrison predicted. The call goes out at midnight Chicago time. Harrison's phone rings. He answers on the second ring. He's been sleeping, lightly waiting for this. Elena's voice. Harrison, we're seeing it, right where you said. Harrison sits up in bed, his wife Margaret beside him waking. You're certain? Plasma signatures consistent with shock crossing. Voyager 1 is at 85.1 astronomical units. Harrison closes his eyes, breathes. Of course it is. Physics works. You were right. I was precise enough that reality confirmed me, he says. There's pride in his voice. Decades of work validated. Mathematical predictions matching observed data. The highest achievement in physics. He hangs up. Can't sleep. Goes to his study. Pours a glass of whiskey he's been saving. Sits at his desk. On the wall, framed copies of his papers. Dynamics of the interplanetary gas and magnetic fields. 1958. Prediction of the heliospheric termination shock. 1976. He's 76 years old. He's just seen his life's work confirmed by direct measurement 15 billion miles away. This is the moment he's been waiting for. But the moment doesn't last. October 2002. The shock signatures are weakening. Elena notices it first. She's watching the plasma data every day. The sharp increases in particle density and temperature that mark the shock crossing in August, they're fading. By November, they're gone. December 7th, 2002. The data is unmistakable. Voyager 1 is back in supersonic solar wind, as if the shock never happened. Elena calls an emergency science team meeting. 20 people on video conference. Harrison patches in from Chicago. She presents the data. The termination shock signatures disappeared in mid-November. Current readings show supersonic flow. All indicators say we're upstream of the shock again. Silence. Then Harrison's voice tight with confusion. That's impossible. Boundaries are spatial, not temporal. The spacecraft crossed. It should stay crossed. Unless the boundary moved, someone suggests. Shockwaves don't move, Harrison says. Not like this. Not hundreds of millions of miles. But the data doesn't lie. Voyager is no longer in the shocked region. It's back in the smooth, fast-moving solar wind, as if the boundary retreated. 2003 becomes a nightmare for Harrison Webb. The shock signatures return in February. Voyager crosses again. Then in April, they vanish. The boundary retreats again. August at crossing. October retreat. It's not a wall. It's not a static boundary in space. It's breathing, expanding when the sun produces strong solar wind bursts, contracting when the wind weakens. The boundary is moving outward and inward by several astronomical units over the course of months. Harrison can't sleep. He's in his study every night rechecking 30 years of calculations. Where did he go wrong? Margaret finds him at 3 in the morning in December 2000, 3 papers scattered across his desk, his head in his hands. You haven't slept in 3 days. I can't, he whispers. My life's work is wrong. The shock exists, you predicted that. I said it was at 85 astronomical units. Static, a line in space, but it's not static. It's dynamic, moving, breathing. I missed something fundamental. What? Harrison looks up. His eyes are red. I underestimated how violently the solar wind varies. I assumed the interstellar medium was uniform. I treated the boundary as equilibrium between two steady forces. But neither force is steady. The sun pulses. The interstellar medium has structure. The boundary responds to both. Is that wrong? It's incomplete, Harrison says. The word tastes bitter. Incomplete is worse than wrong. Wrong you can fix. Incomplete means you didn't understand the question. Margaret sits beside him, puts a hand on his shoulder. He says quietly, I was so certain. I know. Certainty is a trap for fools. She doesn't argue, just sits with him in the darkness. Outside, the universe continues not caring about human certainty. December 16th, 2004. Voyager, Roger. 1 crosses the termination shock for the last time. The spacecraft is at 94 astronomical units, 8.7 billion miles from the sun. Not 85 astronomical units, 94. 9 astronomical units farther than Harrison predicted. 9 times the distance from Earth to the sun, 840 million miles. The crossing is definitive this time. The plasma signatures hold. Voyager settles into the region beyond the shock, the helios sheath, the turbulent zone of slowed solar wind. It doesn't cross back. The boundary has stabilized farther out. The breathing has stopped, at least for now. Harrison receives the data at home. He's 78 years old. He reads the numbers. 94.0 astronomical units. He closes the report, sits in his study, doesn't turn on the lights. 9 AU error, 10%. In planetary science, that would be acceptable. But Harrison is a theoretical physicist. He doesn't do 10% errors. He does precise predictions that match observation to decimal places. 840 million miles off, like predicting the distance from New York to Los Angeles and being wrong by Kansas. He picks up his phone, calls Elena. I'm taking a sabbatical, he says, effective January. Harrison, I need time to process this. to understand where I went wrong. You weren't wrong. The shock exists. You predicted it would exist. I said 85, Harrison says. His voice is hard, brittle. I wrote it in textbooks. I trained students. I told everyone confidently 85 astronomical units, and I was wrong by 840 million miles. Don't, he interrupts. Don't tell me science is iterative. Don't tell me being wrong is how we learn. I know that. I've known that my entire career. But this isn't a small correction. This is fundamental. I missed something about how the heliosphere works, about how solar wind and interstellar medium interact. And I spent 30 years being certain about something I didn't fully understand. Elena is quiet. Then, what will you do? Disappear for a while. He hangs up. Harrison Webb vanishes from the scientific community for 2 years. He doesn't attend conferences, doesn't answer emails, doesn't publish. His colleagues worry. Some think he's had a breakdown. Others think he's being overdramatic. Science is full of revised predictions. It's not personal. But for Harrison, it is personal. He spends 2005 and 2006 reading everything published about the heliosphere in the last 30 years. Every measurement from spacecraft, every new model, every data point he didn't have when he made his original predictions. He fills notebooks, hundreds of pages, working through the mathematics again from first principles. And slowly, painfully, he finds his mistakes. Not mathematical errors. The equations were right, but assumptions. He'd assumed the solar wind output was more constant than it actually is. He'd assumed the interstellar medium was more uniform. He'd assumed the sun's magnetic field didn't add significant pressure. Small assumptions, reasonable at the time, but small errors compound. Across 8 billion miles, small errors become 840 million miles. In his journal, April 2006, he writes, "Certainty is a luxury only the ignorant can afford. The more you know, the more you realize how much you don't know. I was certain because I didn't know enough to be uncertain. The universe has taught me humility. Expensive lesson. Worth learning." Margaret reads this entry after he's asleep. She cries quietly. Her husband has spent 2 years teaching himself to be wrong. It's the bravest thing she's ever seen him do. August 30th, 2007. Voyager 2 crosses the termination shock. Different location. The spacecraft is heading more toward the flank of the heliosphere, while Voyager 1 went toward the nose. Voyager 2 crosses at 84 astronomical units, not 94, 84, 10 astronomical units closer than Voyager 1, 930 million miles closer. If the heliosphere were a sphere, a symmetric bubble around the sun, both spacecraft should cross at roughly the same distance. They didn't. 10 astronomical units difference. The heliosphere is not a sphere. The data confirms what the theorists have been calculating since Voyager 1's crossing the heliosphere is asymmetric. Compressed on the side where the sun is moving through the galaxy. Extended on the trailing side. Bullet-shaped. Teardrop-shaped. The sun is traveling through the local interstellar medium at 490,000 miles per hour. From the sun's reference frame, the interstellar gas is a headwind. That headwind compresses the nose of the heliosphere where Voyager 1 crossed at 94 astronomical units. The sides are less compressed where Voyager 2 crossed at 84 astronomical units. And behind the tail likely stretches hundreds of astronomical units. They don't live in a bubble. They live in a comet-shaped structure elongated by the sun's motion through space. Marcus Aldrin, 73 years old now, gives a press briefing. His hair completely white, his voice still soft but weighted with decades of wonder. "We thought we lived in a sphere," he says, "a bubble centered on the sun. Symmetric, simple, beautiful. But we don't. We live in a teardrop falling through the galaxy, compressed in front by our motion, stretched behind into a tail we haven't even measured yet." A reporter asks, "Does this change anything?" Marcus smiles, sad smile. "It changes what we thought we knew. That's everything." October 2007, University of Chicago, a public lecture hall, 600 seats. Standing room only. The title on the marquee, "I Was Wrong, What Voyager Taught Me About Certainty." Speaker, Dr. Harrison Webb. He walks onto the stage slowly. 81 years old now. The Parkinson's is visible. His hands shake. His gait is careful. But his mind is clear. He stands at the podium, no notes, speaks directly. "For 24 years, I told you the termination shock was at 85 astronomical units from the sun. I published papers. I wrote textbooks. I trained graduate students. I gave lectures with confidence. I said, mark my words, 85 AU. Pause. I was wrong by 840 million miles. The audience is silent. That's not a rounding error. That's not close enough. That's wrong, fundamentally significantly wrong. Another pause. He grips the podium. His hands shake. I could tell you the science, how the solar wind varies more than I accounted for, how the interstellar medium has structure I ignored, how magnetic pressure matters more than I calculated. I could explain where the mathematics was incomplete, but that's not why I'm here. He looks out at the audience. I'm here to tell you that being wrong isn't a failure. Being unwilling to revise when data contradicts you, that's failure. Someone in the front row starts clapping. Then another. Then the whole room. Harrison waits for silence. The universe doesn't care about our models. It doesn't care about our equations. It is what it is. Our job isn't to be right. Our job is to listen better, to measure more carefully, to revise constantly, to hold our certainties lightly. He's crying now, not hiding it. I spent 30 years certain about something I didn't fully understand. Voyager taught me humility. 840 million miles of humility. It's the most valuable lesson I've ever learned. Standing ovation. 4 minutes. In the audience, Marcus Aldrin, Elena Vasquez. Rachel Dimitri, now 56 and a senior administrator at JPEL. Marcus is crying too. After the lecture, he approaches Harrison. They haven't spoken in 2 years. I'm proud of you, old friend, Marcus says. Harrison grips his hand. I'm proud of the universe for being more interesting than I gave it credit for. They stand there, 2 old men, both in their 70s, both witnesses to humanity pushing into the unknown, both learning the same lesson: the universe is always stranger than we imagine, always more complex, always one step ahead. And that's not frustrating. That's wonderful. 2010. Voyager 1 is in the heliosheath, the region between the termination shock and the heliopause, the true boundary where the sun's influence ends. The spacecraft is 106 astronomical units from the sun, nearly 10 billion miles. The signal takes 14 hours and 40 minutes one way. Elena Vasquez is 69 years old, still working, still monitoring Voyager every day. She's watched this mission for 33 years, longer than some of her colleagues have been alive. And something is wrong with the data. Cosmic rays are increasing. Slowly, steadily, these are high-energy particles from outside the solar system. Supernova remnants, exploding stars, violent events across the galaxy. The heliosphere shields us from them. The solar wind and the sun's magnetic field deflect them, slow them down. Inside the heliosphere, cosmic ray intensity is reduced. But as you approach the heliopause, the true edge cosmic ray intensity should spike. Sharply, suddenly, that's the theory. But Voyager's cosmic ray detectors are showing a gradual increase, starting at 106 astronomical units. Slow rise, steady. This shouldn't happen. The increase should be sharp. At the heliopause, not before. Elena brings it up in the weekly science meeting. Cosmic rays rising earlier than expected. We're still in the heliosheath, should be relatively constant here. Sharp spike at heliopause. Harrison Webb, now 84, participates remotely from Chicago. His voice over the speaker, how gradual, 2% increase over 6 months. That's not noise. Statistically significant. Silence on the call. Then Marcus Aldrin, 76, from his home in Pasadena. The heliosheath is more porous than we thought. Or thicker, someone suggests. Or the heliopause is not a sharp boundary, Elena says quietly. No one wants to accept that. The heliopause should be clear, definitive. The place where solar plasma stops and interstellar plasma begins. A boundary. But if cosmic rays are leaking in gradually over tens of astronomical units, maybe the boundary isn't sharp. Maybe it's diffuse. Maybe they're wrong again. 2011. The power crisis is real now. The RTGs are producing less electricity every year. Inexorable decay. Can't be stopped. Can't be reversed. Elena runs the projections. 6 to 8 years of science operations left. Then the power will drop below the threshold needed to run the transmitter. Decisions have to be made. Which instruments to shut down? Which to keep running? The planetary radio astronomy instrument goes first. Designed to study radio emissions from planets. But there are no more planets. Haven't been for 30 years. Elena executes the shutdown command in March 2011. Alone in her office, midnight. She types the command. Waits 14 hours and 40 minutes for it to reach the spacecraft. Waits another 14 hours and 40 minutes for confirmation. When the telemetry confirms the instrument is off, she writes in her log, shut down PRA today. Felt like Killing part of Voyager, like choosing which limb to amputate. Necessary. Still hurts. She doesn't tell anyone she cried. May 2012. The cosmic rays are still rising. Faster now. 5% increase over the last 6 months. At the same time, solar particles, protons, and electrons from the sun are dropping. Not sharply, gradually, like a slow fade. The team is confused. These changes should happen at the heliopause, together, suddenly. Cosmic rays up solar particles down magnetic field rotation, all at once. But this is gradual, progressive, like walking into fog rather than crossing a line. Rachel Dimitri visits JPL. She's 61 now. Semi-retired, still consulted on major mission events. She sits with Elena looking at the data. I've seen this before, Rachel says, where Io, right before the volcanoes erupted. The data didn't fit the models. Everyone was confused. Then boom, discovery that changed everything. Elena looks at her. You think we're about to discover something? I think when data doesn't fit, the universe is about to teach us something huge. Elena nods slowly. I hope I'm alive to see it. You will be, Rachel says. Voyager won't let you go until you understand. They sit together, two women who've given decades to this mission, both sensing they're on the edge of something, neither knowing how close they are. June 28, 2012. Voyager 1 is at 120 astronomical units, 11.1 billion miles. The magnetometer data shows something extraordinary. The magnetic field lines, which have been tangled and twisted throughout the Helios sheath, chaotic from the turbulent solar wind, suddenly align, perfectly straight, radially outward from the sun. No twisting, no tangling, as if someone drew them with a ruler. And particles are flowing along these field lines, both directions. Solar particles flowing outward. Galactic cosmic rays flowing inward. Like a highway, a magnetic highway connecting the inside to the outside. Elena sees the data first. She stares at her screen for 10 minutes. Then she calls an emergency science team meeting. 47 people on the conference call within 2 hours. Elena presents, the magnetic field has organized into perfect radial alignment. Particles flowing bidirectionally. Solar wind escaping. Cosmic rays entering. The field lines appear to be connected.